When we think about computer security, our minds usually jump to things like passwords, maybe firewalls. But what if I told you the real rules are hidden way deeper than that? See, underneath it all, there's this kind of fundamental grammar that dictates how information is even allowed to move around. So in this explainer, we're going to peel back that layer and look at the verifiable goals that actually make modern security work.
Okay, so picture this. You download some cool new app. Maybe it's a photo editor, maybe it's a game, doesn't matter. And hey, it seems to work great. But what you don't know is that hidden deep inside its code, there's a little spy, a piece of malware that's quietly copying all your private files and shipping them off to some attacker. So the big question is, how do you possibly stop a threat that you've already let inside the gates?
And that right there is what we call the Trojan horse problem. It points to this really critical flaw in how we usually think about security. See, your standard permissions, they're just not going to cut it here. A Trojan horse doesn't care about your password because you ran the program. It's using your permissions to do its dirty work, which means it can see everything you can see. To stop something like that, you need a higher authority. You need a rulebook that's built into the system itself, one that even you can't just bypass.
And that idea, that hidden rulebook, is really the core solution we're talking about today. It's what's known as a mandatory protection system. So let's break down what that actually means.
All right, think of it this way. In most systems you use every day, you're the boss of your files, right? That's called discretionary access control. It's at your discretion. But in a mandatory system, that's not the case. The operating system is the boss. Period. It goes around and slaps these unchangeable labels on everything, on you, on your programs, on your files. And then it enforces this super rigid policy about how things with different labels are allowed to interact. And the key thing here, it's tamper-proof. You, the user, can't change the rules.
Okay, so how in the world does a system even start to build a rulebook like that? Well, it all boils down to one surprisingly simple but incredibly powerful idea. You just have to map out the flow of information.
Yeah, it sounds complicated, but the basic idea is really straightforward. Information flow is just a fancy way of saying we're watching where the data goes. So, when a program reads the file, information flows from the file to the program. Easy. When it writes to a file, the information flows from the program to the file. That's it. By just tracking those two simple actions, reading and writing, we could start to build a map of every single potential path that data could take through the entire system.
And this is what that map looks like under the hood. It's called an access matrix. It's really just a big table, you know? On one side, you have the subjects. That could be you or a program you're running. And across the top, you have the objects, which are usually files. The table just spells out exactly who can do what to whom. So you can see here, subject S1 can read one file and write to another. Subject S2 can only append things. It's basically the system's complete cheat sheet for every single allowed action.
Now, a table like that is great for the computer. But for us humans trying to find security holes, it's a bit of a nightmare. So what we can do is transform that table into something much more useful, a visual map, a graph. Every read permission becomes an arrow showing data flowing from a file to a program. And every write is an arrow flowing out from a program to a file. Suddenly, you've got this visual map of all the potential data flows, and that is incredibly powerful, because now you can actually see where a secret might be able to leak.
Okay, so we have our map. Now let's put it to work. We're going to tackle our first big security goal, secrecy. How do we use this map to make absolutely sure that our secret information doesn't wind up in the wrong hands?
The goal here is pretty simple, right? We just want to control the flow of info to keep things confidential. And with our information flow map, we can now do something really cool. We can mathematically prove whether there is any possible path, even a weird indirect one, from a secret file to a user who shouldn't see it. If we find even one of those paths, boom, the system is insecure. So, the way we do this is by creating what you can think of as a ladder of secrecy. We slap a label on everything. At the bottom, you have unclassified, then maybe confidential, then secret, all the way up to top secret. And here's the one simple rule. Information is only ever allowed to flow up the ladder, never ever down. So sure, you can use unclassified info to write a confidential report, but top secret data, no way is that ever leaking down into an unclassified file.
And this whole idea brings us to a really famous security model called Bell-LaPadula, or BLP. It has two main rules. The first one is super intuitive. It's called no read up. If you've got secret clearance, you can't just open up a top secret file.
Makes sense. But the second rule, this is the really clever one. It's called the star property, or simply no write down. This says that a program that's handling top secret data is physically forbidden from writing to any file at a lower security level, and that is how you stop the Trojan horse. Even if that malicious code is running with your permissions, the system itself steps in and says, nope, you're handling secret data, you are not allowed to write that out to an unclassified file. The leak is blocked at the source.
But, security isn't just about keeping things secret. It's also about making sure your data is trustworthy, that it hasn't been corrupted. And that brings us to the perfect mirror image of secrecy: integrity. With integrity, the goal is totally different. We want to make sure that our really important, high-integrity stuff, think critical system files, doesn't get messed up by low-integrity junk, like some sketchy program you downloaded from the internet. We're trying to prevent contamination.
So to do this, we get another famous model, the Biba integrity model, and its rules are the exact opposite of what we just saw. First, you have no read down. This means a super important, high-integrity program is forbidden from even reading from a sketchy, low-integrity file. It can't get contaminated. Then you have no write up. A low-integrity program can't modify a high-integrity file. It's a perfect, beautiful inverse of the secrecy rules.
And that's really the whole thing in a nutshell. When you're talking about secrecy, information can only ever flow up the ladder. But for integrity, information can only ever flow down. They are literally two sides of the very same coin, and you need both of them to create a truly secure system. Okay, so these models sound pretty bulletproof, right? We've controlled all the reads and writes, but what happens if information finds a sneaky way to communicate that doesn't involve reading or writing files at all? This is where we run into the tricky problem of covert channels. These are these really sneaky back alleys for communication that our security model just doesn't see. They don't use files or messages. Instead, they exploit shared physical resources, side effects of how the computer actually works. And because of that, they exist completely outside the control of our beautiful, formal models.
Let me give you a couple of classic examples. Imagine a storage channel. A top-secret program wants to send a single bit, a 1 or a 0. To send a 1, it just fills up the entire hard drive with temporary files. To send a 0, it leaves it empty. Now, an unclassified program can't read the secret files, of course, but it can easily check, is the disk full? There's your leaked bit. Or think about a timing channel. The secret program sends a 1 by running a super intense calculation that hogs the CPU and makes the whole computer feel sluggish. It sends a 0 by just sitting idle. Another program can just time how long things take to figure out the secret message. And these things are incredibly hard to stop.
All right, so let's zoom out for a second and pull all of these pieces together. What's the big picture here?
So let's recap the key takeaways. At the absolute heart of all of this is tracking information flow. That's the key. For secrecy, using models like Bella Padula, we make sure information can only ever flow up. For integrity, with models like Biba, we make sure it only ever flows down. A crucial point is that these models are super conservative. They block any potential bad path, not just ones we know are being exploited. And of course, the whole system is constantly being challenged by those sneaky little covert channels. And really, that gets to the whole philosophy behind this kind of security. Look, these models aren't a perfect reflection of reality. They're powerful approximations, but they are designed from the ground up to be safe by default. The system would much rather block a legitimate action that looks even a little bit sketchy than risk allowing a malicious one to get through. It is the ultimate better safe than sorry approach to building a secure system. Which kind of leads us to the big final question. These models we've been talking about, Bella Padula and Biba, they're from decades ago. I mean, they're elegant, they're logical, they're mathematically beautiful. But in our world today, with super complex software, everything constantly connected to everything else, and now AI in the mix, is this beautifully simple, almost rigid view of information flow, is it still enough? Well, that is one of the biggest and most interesting questions in computer security right now.